So to begin with this particular lecture, let's start with the 3-input NAND gate where I'll also pick my pointer, and the 3-input NAND gate where with logic of 110, what should be the gate leakage current and what should be the subthreshold leakage current. So if it is actually 110 here, we know that this being on going to act like a pass transistor. So on one side it is VDD, so it is going to pass it a VDD minus VT here. And this being the transistor also being on, so it is going to pass the VDD minus VT into the other side of the diffusion. The C transistor is the one which is off, so I'm going to get the subthreshold leakage current coming from the C transistors. So the subthreshold leakage current, where one side it is VDD minus VT, the other side it is 0. So I will have 10 raised to minus 3 multiplied by I off. So it is nothing but 0.501 multiplied by I off. I off of the NMOS transistor is nothing but 5.63. That has been characterized or given in the data sheet. We will get 2.815 nanoamperes as the subthreshold leakage current that will be flowing across these 3 transistors, although it is kind of defined by the C transistor. The gate leakage current here, is we need to identify which of the transistors are really on, and then try to identify the gate leakage current from that on transistor. So these 2 transistors are actually on, but because my VGS value turns out to be actually be low, very low, that is nothing but VT value. So my gate leakage current in both these cases will be 0. So I will have a gate leakage current of 0 here. Right, so in this particular logic, we will have 110. We have even on the PMOS side, we will not have any subthreshold leakage current, and then the gate leakage component, although it is a 0 transistor here, which means it's a non transistor on the PMOS side. The gate leakage current in the PMOS side is considered to be 0, so we will not have any gate leakage current. We will not have any subthreshold leakage current coming from the PMOS transistor side or the pull-up circuit. On the pull-down circuit, we will have a gate leakage current of 0 and then the subthreshold leakage current of 2.815. So my static power will be nothing but 2.815 multiplied by 1 volts, which will be nothing but 2.815 nanowatts. So hope this is clear. Moving ahead, if I have a logic of 111, then I will have this on the NMOS side, I will have all the transistors to be on. So my subthreshold leakage current will be 0. And on transistor is going to give me the gate leakage current because on one side, the output terminal node is 0. So all the transistor is going to yield or going to give us the gate leakage current, and the gate leakage current because it is 0. So I will have a 0 here, I will have a 0 here if I consider it to be a pass transistor, and then I will get a VGS value for all the 3 transistors to be nothing but VDD. So I will get a gate leakage current for the A transistor, for the B transistor and C transistor. So the overall gate leakage current on the pull down side will be nothing but the gate leakage current of the A transistor plus B plus C transistors. So it will be 3 times the gate leakage current for an NMOS transistor. So it is nothing but 3 multiplied by 6.3, which will be 18.9 nanoamperes. The subthreshold leakage current, because of the pull down side, all the transistors are on, so I will not have any subthreshold leakage current coming from the pull down side. Whereas on the pull up side, I will have all the 3 transistors to be off because the logic of 1 is applied here. So I will have an off transistor here, I will have an off transistor here, and I will have an off transistor on the C transistor on the PMOS side as well. So this off transistor is going to yield or going to give us, the individual, because all these 3 PMOS transistors are in parallel. So we will have an individual subthreshold leakage current. We will have an individual subthreshold leakage current. We will have an individual subthreshold leakage current. So the subthreshold leakage current will be nothing but 3 times the I off of PMOS. I off of PMOS is 9.3. So 3 times 9.3 will be 27.9 nanoamperes. So the total of this will give me the total leakage current, and multiplied by 1 VDD 1 volts will give us the total static power for this particular logic of 111. Right, moving ahead. So let's take a look at the 2-input NOR gate, because this will give us some analysis towards the PMOS side subthreshold leakage current and how do we evaluate the static power. So for a logic of 0, 0 here, so that means on the pull down side, I have a logic of 0, 0. So both these transistors are off. So my gate leakage current will be 0 coming from the pull down side. And the gate leakage current on the pull up side is anyway 0, because that is what we have been assuming. So the subthreshold leakage current here will be coming from one transistor, because my output logic here is nothing but 1, because both these transistors are on, and it's going to drive the output logic to a logic level of 1. So my subthreshold leakage current will be nothing but coming from two independent off transistors. So it will be twice that of the I off of NMOS. I off of NMOS is nothing but 5.63. So multiplied by 2 will give me 11.26 nanoamperes. The gate leakage current is anyway 0. Because these two transistors on the pull up side are on, so I will not have any subthreshold leakage current coming from the pull up circuit. So my overall, the static power will be nothing but 11.26 nanoampere multiplied by 1 volts, which will be 11.26 nanowatts. Moving ahead, if I have a logic of 1, 0. So if I have a logic of 1, 0 here, we know that the output will be pulled down so that the output will be 0 here. And I will have a gate leakage current coming from this on transistor because the VGS value here is nothing but, the 1 volts. So I will have a gate leakage current of the of the NMOS transistor, which will be 6.3 nanoamperes. The B transistor is off here, so I will not have any gate leakage current coming from the B transistor on the pull down side. But even that, the subthreshold leakage current because of the off transistor will also not be there, because on one side I will have a 0 voltage, on the other side also I will have a 0 voltage. Since the VDS for the B transistor on the NMOS side is 0, I will have the subthreshold leakage current coming from the off B transistor on the NMOS side will also be 0. On the pull-up side, there is one transistor which is off and the other transistor which is on because of the 1, 0 logic. And so because this is the on transistor and on the other side of the diffusion it is 0, so this particular node will be discharged to VT. So if I have a y is equal to VDD, right? So and then it is kind of discharged to 0. So this particular node value will have some particular higher node voltage, and while it is discharging through this the pull down side, it will limit itself to VT. So it cannot further reduce more than VT value. Otherwise, this channel will not be there. So it will be limited to VT, and that's what the PMOS pass transistor works like, right? So if it is 0 on this side, it is going to have or limit the voltage of VT on the other side. And if I have a VT voltage here, right, then I should be able to find out the subthreshold leakage current, which will be nothing but having a potential difference of VDD minus VT. On the PMOS side, it will give me 0.501 I off of PMOS. So it will give me I off of PMOS is given as 9.3 nanoampere, so it will give me 4.65 nanoamperes of subthreshold leakage current, right, coming on the pull-up side. The gate leakage current, is anyways on the PMOS side is negligible, so it is considered to be 0. So finally, I will have a total gate leakage current of 6.93 nanoamperes and a subthreshold leakage current of 4.65. If I add this up and then multiply by 1 volt, I'll get the static power. Moving ahead, logic of 0, 1. So if I have a 0 and 1 and 0 and 1 here, so on the pull down side, I will exactly have the same things as that of on the previous slide. So the gate leakage current on the NMOS side is now coming from the B transistor. The subthreshold leakage current for the A transistor is anyway 0, because on both the sides of the diffusions, it's the same potential. So the potential VDS for the transistor A is 0, and hence the subthreshold current will be 0. Now, because this is 0 and 1 here on the pull up side, the 0 makes this A transistor on, and it is going to pass the VDD voltage onto the other diffusion side. And this particular off transistor, because it sees a VDD value here and then the output node as 0 here, I will get an I off of PMOS as a subthreshold leakage current. The I off of the PMOS is nothing but 9.3 nanoamperes. So my total leakage current will be 9.3 plus 6.3 multiplied by that of 1 volt will give me the static power. Moving ahead, if I have a logic of 1, 1, so that means 1 and 1. So my output node is pushed or pulled to 0 volts. So having a 1 and 1 here will not have any kind of the subthreshold leakage current on the pull down side. I will have only the gate leakage current, and the gate leakage current coming from the two transistors will be nothing but 2 into the Ig of the the gate leakage current attributed from the NMOS side. So it will be 2 times the 6.3 nanoamperes, which will be 12.6 nanoamperes. Both these transistors are off on the pull up side. So I will have the subthreshold leakage current coming from the PMOS transistors, which is actually derived in the next slide. So it turns out to be very, very similar to that of the 0.1199 of the I off, which we have deduced for the NMOS transistors. So it turns out to be 1.115 nanoamperes. So the total leakage current will be nothing but this plus this. And if I multiply by 1 volt, I'll get the static power. So now in the next slide, we will have a look into this particular derivation for the PMOS transistor. Although it is very, very similar to that of the NMOS transistor, so I can quickly go over it. So the subthreshold leakage current or an expression for the subthreshold leakage current for a PMOS transistor is very, very similar to that of the NMOS transistors. So if I write the NMOS transistor expression and then compare that, we see that for the PMOS transistor, instead of VGS, it is VSD. And this is eta and the subthreshold slope. K gamma is also the same as that of the NMOS transistor. And so this particular, instead of VDS, it is now written as VSD. And instead of VSB, it is now written as VBS. Right? So the expression remains the same. Only thing, the references, the voltage references are being symmetrically opposite. So if I have this particular expression for the PMOS transistor, then having this particular VDD values and then the stacked transistors and then the output node to be 0, we know that this particular subthreshold, subthreshold leakage current for the transistor A will be same as the subthreshold leakage current for the transistor B. Applying this particular Vx variable value and then on the logic level of 1, which is nothing but VDD, into this particular expressions, we should be able to find out the subthreshold leakage current or express the subthreshold leakage current for the transistor A and express the subthreshold leakage current for the transistor B, equate them, and then we should be able to arrive at a Vx value. Turns out to be 0.92101, which is kind of very, very close to 1 volts. And if I remember the 2 stacked transistors for an NMOS transistor, we got the Vx value very, very close to the 0 volts. Here in the 2 stack PMOS transistors, we will get the Vx value very, very close to the VDD value of 1 volts. So that's the difference. Once I have the Vx value, I should be able to find out the subthreshold leakage current, putting into one of those equations of I sub 1 or I sub for the transistor A or I sub for the transistor B. Turns out to be very, very close to 1199 of the I off value. So it is 1.117 nanoamperes for the PMOS transistor. Remember that the I off value of the PMOS transistor is different than that of the I off transistors of NMOS. In fact, the I off of the PMOS transistor is slightly higher than that of the I off of the NMOS transistor. Right, so this completes our evaluation for a given circuit. How do we evaluate for a different input combinations? What should be the static power? So now let's take a very an example on a system side. So the system side means we have been given a design wherein we have 10⁹ transistors being used in the chip. And in the chip, there is 2 designs: logic devices, logic component, and the another is the memory device. So this logic devices will help is designed for the computational part, and then the other set is the memory devices. So out of this 10⁹ transistors, we have 15 to 10⁶ transistors used for this logic purpose, used for designing this computational purpose. The remaining 915 to 10⁶ transistors are used for the memory purpose. The width that is being designed for the transistors is 12 lambda for the logic purpose. Width for 4 lambda is being used for the memory design. And this width is kind of useful to, while we're estimating the currents. So I'll come to that particular current. The activity factor of 0.1 and 0.02 is given, although, if you are trying to evaluate the static power, the activity factor doesn't have any role. The activity factor is actually useful only for estimating the dynamic or the switching power, right? Not in the static power. And the another data is given that in the memory devices, all of them are low leakage devices. So in fact, low current leakage devices. And in the logic devices, 95% of the logic devices or the transistors that has been used is of low leakage devices. So low leakage means low leakage current devices. That means I will use the design has used a higher VT cell. The VT cell is high, so that I'll get a low leakage current. If you remember the exponential term in one of the previous lectures, where we had said that the subthreshold leakage current was a function of exponent of VGS minus VT0, where that VT0, if it was low, I got a high leakage current. If the VT0 was high, I got the low leakage current. So similarly, the 5% of the transistors that has been used for the logic devices, which is 15 to 10 raised to 6 transistors, out of that 5% is been built using the high leakage devices. That means high leakage current. So high leakage current, that means I will have a VT 0 to be low. Right. So what it means is this design has been done 95% of the time caters to the low leakage current, and then 5% it is very, very essential, and that's why they have gone for the low VT0. Remember that the low VT0 will give me the current, the long channel current model. If I estimate the saturation current, and then the linear current will be higher, right? But 95% of the time it is the low leakage current. And if I consider the low leakage current, it is nothing but 10 nanoampere, which is for the high VT cell, and for the low VT cell it is giving me 100 nanoamperes per width of the transistor. So it is actually characterized in terms of the leakage current per the width of the transistor. So that's why the micron is given here. So 100 nanoamperes per micron. So for a transistor, if I want to evaluate if it's a transistor of low leakage devices, which has used the high VT0. So the low leakage devices will have 10 nanoamperes per micron multiplied by what is that width of the transistor. So the width of the transistor is 12 lambda, where lambda for a 65 nanometer technology node is nothing but 25 nanometers. So I'll have to express this in microamperes, so 0.025 microamperes. All right. So hope this particular statement is clear. The example of the system design is clear. Also, one more characteristic is given is the gate leakage current for an NMOS transistor is 5 nanoamperes per unit micron. Right. So in this particular case, let's try to find out what should be the subthreshold leakage current for the logic device first, and then try to calculate the subthreshold leakage current for the memory devices, and then calculate what is the gate leakage current for all the logic as well as the memory devices. And then try to combine both of them and then evaluate the static power. The subthreshold leakage current for the logic device here, the logic device is this, and out of 15 to 10 raised to 6 transistors, 95% of time it is going to use the low leakage current, which is 10 nanoamperes per micron, and 5% of the time it is going to use the 100 nanoamperes per micron. So out of 15 to 10 raised to 6, 95% is going to use 10 nanoamperes per micron, and only 5% is going to use 100 nanoamperes, and multiplied by the width, which is 12 lambda. So 12 multiplied by 0.025 should be able to give me the overall subthreshold leakage current for the logic devices. Right. Similarly, if I can evaluate or estimate the memory devices and then the subthreshold leakage current for the memory devices, which will be nothing but 915 to 10 raised to 6, and all of them uses the low leakage devices. So 915 to 10 raised to 6 multiplied by the width, which is 4 lambda, 4 into 0.025 multiplied by the low leakage devices characterized by 10 nanoamperes per micron. So if I do that, I'll get 0.95 amperes. Right. So if I go back, I used to get for the logic devices it was 0.2175. For the memory devices it is 0.95 amperes. So total subthreshold leakage current is nothing but accumulate both of them, and we will get 1.1675 amperes. Right. Note the unit is amperes, because although it is a nanoamperes, that is what is defined here. Right. It is the number of transistors which in the design which essentially accumulates to the ampere value. Right. So the last one, so the gate leakage current for the logic as well as the memory. So the 915 to 10 raised to 6 and a 15 to 10 raised to 6. Right. 950 into 10 raised to 6 of the memory devices has a width of 4, And 15 to 10 raised to 6 transistors has a width of 12 lambda, 4 lambda and 12 lambda. So that is what is written here, multiplied by the gate leakage current, which is characterized as 5 nanoamperes per micron. So my gate leakage current for both logic and memory is 0.55 amperes. Right. So now I have the gate leakage current and then the subthreshold leakage current for this overall system design, which uses 10 raised to 9 of the transistors. Then we should be able to evaluate the static power. Now remember that while we are considering the gate leakage current and the subthreshold leakage current, the transistors which are off are contributing towards the subthreshold leakage current, and the transistors which are on are contributing towards the gate leakage current. Right? So if I want to accommodate both the gate leakage current and then the subthreshold leakage currents, we have to ensure that we have to assume something. If it is not given, we have to assume something that one assumption that we can make is 50% of the transistors, 50% of 10 raised to 9 transistors which have been used to design this system, we can assume that they are contributing towards the gate leakage current. So that means that they are on. And the remaining 50% of the transistors, of the 10 raised to 9 transistors, are off and they are contributing towards the subthreshold leakage current. So with that assumption, we can estimate the overall total current. The total current turns out to be the gate leakage current 50% of that, and then the subthreshold leakage current 50% of that, because 50% of them are on and that they will contribute towards the gate leakage current. 50% of the transistors are off and they will contribute towards the subthreshold leakage current. And if I do that multiplied by the VDD, I should be able to find out the static power. Static power turns out to be 0.85875 watts.